Thank you very much for the introductions and your invitations. So my name is Quoc-Tung, and I'm a PhD student from ENS Lyon, France. And so today's topic is roughly my PhD thesis, and it titles the Algorithmic and Theoretical Aspects of Sparse Deep Neural Networks. So I guess the sound is okay, and all of you see my screen.
Yep, it's perfect.
Okay. So firstly, I want to first mention my collaborator. So on the left, Leong Zhang, another PhD student from my laboratories, and the other two as my supervisors. So as suggested by the title, today I'm going to talk about deep learnings. And so it's so nowadays you see that deep learning is extremely dominant in the fields of machine learning and artificial intelligence. However, it comes with a price. So deep learning is very powerful under some requirement. So here's I lead three components that I think is very important for the success of deep learning models. First, we need huge parametric models, and in this case, neural networks with a lot of layers. And if the total numbers of the parameters is bigger than its training set, then we call the models over parameterized, or in the regimes of over parameterization. And then to train the huge model, you need like a massive data set as well, whether it's the data set of voice, documents, or image. And finally, to run the algorithm to fit the training sets to our models, we need a lot of computing resources, and in this case, a large number of GPUs. So here's some evidence for my argument. So already at January 21, we already have a model that had up to trillions of parameters, and now we already is at 23. So I think these figures are already outdated. The same phenomenon happen for data sets. So in the 80s, last training sets had like hundreds of data points, but now most of the popular data set for large language models, it contains up to billions or even trillions of data points. And finally, to train the state-of-the-art model in deep learning, we need a lot of GPU. So here's it say that in minimum we require like 500 of state-of-the-art GPU to be able to tune like very large deep learning models. So so the information suggests a very natural question. So the growth of these three components are very exponential. So can we somehow make the three components become more scalable? So people in the communities, so they come up with an idea that is to use the notion of sparsity or sparse deep neural networks. And here's I assume that all of you were somewhat familiar with the notions of deep neural networks. So in comparison to the usual deep neural network, so sparse deep neural networks are essentially the same, but in each layer, we require the weight matrices to be sparse. So it means it had a lot of coefficient that is equal to 0. And so some problem that we have with the conventional deep neural networks, it usually trained in the regimes of over parameterizations. So we need a lot of space to store all the parameters, and to fit the model, we need large training sets to make it generalize well on unseen data. And finally, empirically, people observe that if we use very large neural networks, it usually memorizes perfectly the training data. So if the training data is somewhat sensitive, like medical records or something like that, it might lead to some privacy issue. And sparse deep neural networks, it offer remedies for all these shortcomings. Because, for example, now we have a much smaller parametric model if our weight matrices have a very high sparsity level. And because now we have fewer parameters to learn, intuitively we need fewer training data to fit the model. And we are no longer in the over parameterization regime. So very likely that we do not memorize anymore the training data, and that reduce the privacy issue. So the question is now, how can I train a sparse neural networks if that's good? Here's just a reminder that a deep neural networks is parameterized by theta. So it's the set of weight matrices and bias vectors of each layer, and given a vector x, the neural networks will output something by computing the products wx plus b, followed by an activation function sigma, and usually this sigma is chosen to be nonlinear. And so we have two types of network. On the top is sparse neural networks, and on the bottom is the usual, the conventional deep neural networks. And to fit the model, it to solve an optimization problems. And the only difference between the dense and the usual and the sparse neural networks is I want to promote the sparsity of the weight matrices WI. So that the only difference between the two optimization problems. So we want to study the problems. However, it's quite complicated in the sense that we have nonlinearities in the activation functions. So one way to have a simpler model to analyze is to switch the activation function to linear one. So now we just consider sigma to be an identity functions, and that make the optimization problems much simpler to analyze. And so that's the spirit of our analysis. And with that in mind, we now consider several questions that involve with the sparse neural networks. For example, so we have a training problems that on optimization problems. So the first question is, does this problem actually have an optimal solutions? And if it does, there's a polynomial algorithm to train sparse neural networks. And we can also look at the question like the property of the landscape of the objective functions, like we study the property of global minimum, local minimum, something like that. And the strategies is, first we look at the linear version, and then we use the result to somehow try to address questions in the setting of nonlinear activation functions. And when we try to analyze the linear setting, we notice a problem that is very interesting called sparse matrix factorizations. So in these problems, so given a matrix target A and some set of sparse matrices EG, we want to find the matrices or the factor WJ, so that the products of all the matrices or the factors approximate well the target matrix A. And these settings, it can be casted at an optimization problems. And it's a very generic frameworks because we can somehow put our knowledge into the set EG. For example, we can choose EG to be the set of k sparse per row. So that means for each rows, it had at most k non-zero entries. EG can be k sparse per column or k sparse in total. So it's very generic and flexible. And our claim is that the optimization problems of linear sparse neural networks is very similar to sparse matrix factorizations, because the only difference is now you have another bias vector to optimize in the case of linear sparse neural networks. And that's it. And more than that, we also identified a special case of sparse matrix factorization that is even simpler to analyze. And that's we only consider two factors, and E1, E2. It's just the set of matrices who support included in some given set I and J. And we call it variance fixed support matrix factorizations, or in short, FSMF. And here's to be more clear, to be clearer here. So imagine that you have a target matrix A, and we have some subset of the matrix index that is in yellow square, and I want to optimize the coefficient inside the yellow square, and coefficient outside had to be set to 0. And I want to optimize so that A will be very close to the products of X and Y. And in that case, we call I and J as the support constraint on the factor X and Y. Okay, so this is the recap of our reasoning. So we start from sparse neural networks, and we have 3 questions that we want to address, but it's a bit complex to analyze. So if we relax it by using linear activation functions and we use no bias, it's equivalent to the sparse matrix factorization. And if we also have the access to the knowledge of the support of the weight matrices, this is fixed support matrix factorization. And actually, in the case on the left, we know how to answer all the questions, and then we will use the result to answer some question in the case of sparse deep neural networks, and in this case, the existence of optimal solution. So we do not pretend to be able to answer all the questions in the setting of sparse deep neural networks, but we can answer some of them. Okay, and also the sparse matrix factorization is also a problem that is interesting on its own, because if one can approximate a matrix A by products of sparse matrices, then we can accelerate the evaluations of A times a vector X. And this is the principle behind the fast Fourier transform, because the matrix corresponding to discrete Fourier transform can be factorized into log n factor, and each factor has big O of n non-zero entry. And so you have n log n fast algorithms. Another setting that it might be interesting is dictionary learnings, where we represent the data set at a large matrix, and now we want Y, and we want to decompose Y into products of D, the dictionaries, and X, sparse matrices. So in general, we want to find a dictionary that can represent any data points at its sparse linear component. So the plan of the talks is, first I will present some of the results on fixed support matrix factorizations, and then we use the result to study the question of the existence of optimal solutions in the training problems of sparse ReLU neural networks. And finally, we study the so-called butterfly parameterizations approach that is used in sparse deep neural networks. So up to this point, is there any questions? Is there something not clear?
No, it all seems good.
Okay, so we continue, and with the first part, I'm going to talk about fixed support matrix factorization, and in short, I will call it FSMF. So we have 3 questions to address for this problem. So first is the existence of optimal solutions. Second is the question of tractability, and the third one is about the landscape of the functions, the objective function L, X, and Y. So for the existence of optimal solutions, we can find a very simple counterexample to show that, in fact, FSMF do not always admit an optimal solutions. So a simple counterexample is to consider I and J corresponding to the set of coefficients below and upper the diagonals, and two factors are square factor, X and Y are square matrices. So here we choose n equal to 2, and we choose A equal to this binary matrix, and we can show very easily that FSMF had an infimum equal to 0, because it's very easy to find xk and yk so that their limit converges to A. So the infimum is 0, but the infimum is not attained because here this is actually equivalent to the NU decomposition problems in linear algebra. And we know that for some matrices, they do not have the NU decomposition. So this is the classical results in the books, matrix computations. And so we try to understand why these phenomena happen. And so we, instead of solving these problems, an optimization problem with respect to the parameter of X and Y, we do some chain of variables. So now instead of optimizing with respect to X and Y, we optimizing with respect to a matrix B, with the constraint that B belongs to a set Pij. So Pij is defined as the set of matrices that admit the factorize into X and Y. X and Y had the support included in I and J. And all of a sudden, these problems equivalent, the FSMF is actually equivalent to the problem to project a given matrix A onto the set of P and J. And the necessary and sufficient condition for the optimal solution to exist is that the set P and J had to be closed. And a very natural question come to us, and that's the given some subset I and J of the matrix X, can we design the clonist of P and J algorithmically? And here's our ideas to use a very simple topological argument. That's if P and J is closed, then the closure of P and J minus P and J is empty. So this is, I think, kind of trivial one. And the second observation is that the second set, it is actually a semi-algebraic set. So in the end, we just want to decide the emptiness of a semi-algebraic set. So what we can use here is to use the quantifier elimination algorithms, and it allows us to decide the emptiness of a semi-algebraic for any semi-algebraic set. However, the complexity of these algorithms is doubly exponential with respect to the size of the supposed constraint I, J, and the size of the matrix product. So this question is decidable, but for now it's not tractable because there's no polynomial algorithm to decide such a question. So then we look at the another aspect of this problem, that is the tractability, and our results say that for arbitrary support constraint I and J, the problem of FSMF is NP hard to solve. And our proof is based on the reduction between a problem called rank 1 matrix completion to FSMF. So for those of you that are not familiar with rank 1 matrix completion, simply that given a matrix A that I observe some of its entry, and now I want to find the closest rank 1 matrix that match very well the entry that I observe. And this problem, it is shown to be NP hard by Nicolas Gillis and François Guineux in their papers in SciAm journal. However, it's not the end of story, because in reality, usually we deal with problems that have structure, and so we ask ourselves, if we impose some structure on the support ANJs, maybe the thing become better. And we know some of the instance where FSMF had an polynomial algorithms. So the most simplest one is called unconstrained matrix factorization. So in that case, we do not impose any constraint on the supports of X and Y. And so this problem is basically equivalent to find the best ring R approximation of a target matrix A. And this problem is actually used the so-called Euler-Montero's decompositions of a ring R matrices. And algorithm that we use is based on a truncated singular value decomposition. So we compute the SVD, the singular value decomposition, and we take the top R pairs of left and right Asian vector. And our question is, can we somehow use the truncated singular value decomposition to make it work when we really impose the constraint on the supports of X and Y? So to be able to do so, we define a notion called ring one contribution support. So for the case of no support constraint, so we decompose the products of X and Y at sum of some ring one matrices. So here X1, Y1 is actually the first column of X and the first column of Y. And all the summand, their ranks at small ones. And that's the only condition for the summand if there's no support constraint. However, now if I have some support constraint on X and Y, I do the same decomposition, but now the products of X1 and Y1 transpose, it had to be ring one, and it had additionally the constraint on the support itself. And that's constraint on the support corresponding to the Cartesian product between the first column of X, the support constraint of X, and the first of Y. And I call the pink one the support constraint of the X1, Y1 transpose, the ring one support of the first summand. And I do the same thing for X2, Y2, and X3, Y3. And we noted that the special thing about unconstrained matrix factorization is that the ring one support of every summand are identical in the case of no support constraint. And so we generalize this concept, and we give a condition for the set I and J to make the FSMF problems polynomially tractable. And that is, if I and J, it make all of its ring one supports pairwise disjoint or identical, then the corresponding instance of FSMF is polynomially tractable. And to give an intuition why it works, for example, if I have I and J that have 3 ring one support like this, and we can see that the sum of the 3 matrices, 3 ring one matrices, it corresponding to a matrix where the red area, the submatrix in the red area, it had ring 2, because there are 2 components that had the same support at the same position, and the blue matrix submatrix, it had ring 1, because there's only one ring 1 support in the same position. And the algorithm to find the best approximation is to use truncated singular value decomposition for the sub matrices of the target matrix. And that's the question of tractability. And finally, we answer the question about the landscape of the objective functions L X and Y. So here L of X and Y is the Frobenius norm between the difference between the target matrix A and products X and Y. So this problem in general, this function in general is not convex because that X and Y they are not they interact in a way that is not linear. And there's a lot of study had been carried out for these functions, notably to study the property of the local minima, saddle point, and global minima. And these studies have been carried out for linear and shallow neural networks, and also problem that related to matrix factorization, so that matrix sensing, phase retrieval, or matrix completion. So the question that we look at is, what does this landscape look the landscape look like if I impose some constraint on the supports of X and Y? And again, we always look at the most simplest case, where we put unconstrained matrix factorization, and it has been shown that this objective function is not convex, but every local minimum is global minimum, and it had no the so-called spirit local value for any target matrix A. So I won't go into too detail about this notion, but in the spirit of the notion is that for this function, there is no area where if I do gradient descent, I will be stuck in a point that is not global minimum. And question is, do these property still hold in the constraint cases? And the question is yes, it still hold, and we call it the landscape is benign, but it requires some additional assumption. And for us, we say that if the set if I and J is satisfy the condition of theorem 2, theorem 2 is I and J that make the problem polynomially tractable, then the landscape of the objective function, it had no spurious local minima and no spurious local values. So to make a recap on the results with FSMF, we can construct counterexample where FSMF had no optimal solution, and for arbitrary support constraint I and J, the problems can be hard to solve. However, with certain structure on I and J, there exist polynomial algorithms, and under that exactly the same assumption, the loss function of the objective function of FSMF, it had no local minima. And for the followings, we will use the results of existence of optimal solutions and the tractabilities for the following section. Okay. So until now, everything is okay? Is there any question? Something that's not clear?
No, I don't see any questions. It's been good.
Okay. So now we will use the result that obtained in the setting of FSMF to answer several questions in the case of ReLU Sparse Neural Networks. Okay, so here is the optimization problems corresponding to Sparse Neural Networks. So given a dataset D with input X and output Y, we want to minimize the distance between the output Y and the outputs of the neural networks given the input set X, such that the weight matrices of our neural networks belong to some set of sparse matrices. Here, sigma is the ReLU activation function. And in practice, usually we choose EG to be the set of K sparse matrices. So the set of matrices that had at most K non-zero entry. And here we consider quadratic loss for simplification. our argument will work for any cohesive loss function. So it means if the argument go to infinity, I'm sorry, the parameter go to infinity, then the functions go to infinity as well. So the question of non-existence of optimal solution has been studied for several settings, and here we adopt the terminologies ill-posedness. It's adopted from the first paper that studied the phenomena in the case of tensor decomposition, and then the ill-posedness had been studied for several problems, such as matrix completion, robot principal component analysis, or robot PCA, and even classical neural network training. So we ask ourselves, what happens if we consider the training problem of sparse neural networks? So again, our strategy to approach the problem is the same. So instead of considering a generic sparse matrix set EG, we consider EG to be the set where it constrains the support of the way matrix to some given subset of matrix index. So they did give us the fixed support version. And then again, we had the equivalent between closedness and existence of optimal solution. So if we ask ourselves, that is given a support constraint I1 to IN, the optimal solution always exists for any data set, then the response, the condition that is sufficient and necessary is for all input set X, the image of the function that go from theta, the parameters of the network, to the outputs given the input set X is closed. So again, I repeat, this function, it is simply we vary two, I'm sorry, all the parameter Wi and Vi with always with a fixed X, and then the image of this function is closed. So we pick X and we choose all the possible Wi and Vi, and that allows us to establish the first sufficient condition for existence of optimal solution for sparse neural networks, and that is for a two-layer neural networks. That means n equal to 2, and output dimension equal to 1. So that's very important. Output dimension equal to 1. Then any support constraint will make the training problems always admit an optimal solutions, and it leads to a very simple corollary, and it say that again with the same setting, if we choose constraints such as EG to be the set of k-sparse matrices, which is something that used usually in practice, the training problems always admit optimal solutions. And also we show some condition that is necessary for existence of optimal solution. Again, always in the setting of two-layer neural networks with fixed support on the first and the second way matrices. Then the training problem always admit optimal solution if the set Pi and J is closed. So just reminder that the set Pi and J is set of matrices admit the products X and Y, so that X and Y its constraint it supports included in I and J. And this thing is actually decidable, as we show, by using the quantifier elimination algorithms. And this theorem is generalized for deep neural networks, so for arbitrary depth. But now we need to define the set of Pij correspondingly to fix it in the case of multiple layer. But still, the closedness of the new set Pi1 to In is always decidable using the same algorithm. So here, just to emphasize that these conditions is strictly necessary, because there's some counter example that is shown in the paper Blim and his co-author. They say that even if we do not pose any constraint on the support of the wave matrices, then we can carefully construct a data set that had no optimal solution. So again, this condition is strictly necessary. Okay, so and that's and the second part on the existence of the optimal solution for the training problem of ReLU sparse neural networks. So for the last sections, I will going to talk about the so-called butterfly parameterizations in sparse neural networks. So we will start with the discrete Fourier transform. So basically, we want to evaluate the product between the matrix corresponding to the Fourier kernel with some vector x. So usually, if we do a direct evaluation, we need n square, a complexity of n square to compute fn times vector x. However, we have the fast Fourier transform, and that's an algebraic property of the Fourier kernel, and that's in fact, if we just directly evaluate fn times x, we recompute the discrete Fourier transform on even index and the odd index twice. So by calculate it once and keep it in the memories, we can reduce the complexity of the evaluation, and that is the principle for the Kulitzki algorithm with radix 2. So in short, the fast Fourier algorithms. However, if we look at the discrete Fourier transform now from a new point of view, that is matrix factorizations, then we have that algebraic property because the matrix corresponding to discrete Fourier transforms, it can be factorized into 3 matrices. First is a matrix that had four block, each block are diagonal. Second is again a matrix of 4 blocks, but it had a discrete Fourier transform of half side in the diagonal, and the last one is a permutation matrix. So if we keep unrolling this regression from Fn over 2 to Fn over 4, then we can factorize Fn into exactly L factor. So with assumption that n is equal to 2 power of n, followed by a permutation matrix P. And the supports of the factors are very structured. So here I write the support constraint in the binary matrix form. So this is the canonical product between some binary matrix. So it's still a binary matrix, and one coefficient equal to 1, meaning that index in the support, and if that's it's equal to 0, then that index isn't in the support. And so the advantage of the term on the right is that on the left you have n squared coefficient to store in the memory, where on the right there's only n log n coefficient, and that's exactly equivalent to why we have fast Fourier transform of complexity n log n. So that's and for example, if n equal to 16, so equivalently L equal to 4, then we have the support corresponding to all the factor x1 to x4. And you can see that these support are very structured, and people in the community, they call it this is the butterfly structure. Okay, so how can we exploit these kinds of knowledge into the setting of sparse neural networks? So the idea is that in classical neural networks, there are a lot of matrix vector multiplication, a lot of linear operators. So the idea is for any linear operators, I will parameterize the linear operators as a product of butterfly factor. So that help us to reduce the cost of memories and also the cost of the evaluations, because now instead of having n square, we only have n log n parameter to compute, and that's the machineries for the usage of butterfly parameterization. And so it lots of paper based on this principle. So first, butterfly is only 4 square matrices of size 2 power L. However, from time to time, people come up with new ideas, and now it can be generalized to any matrix of any size. And what is very important is that the support of the factor, they are fixed, sparse, and very structured. And now there's a dilemma. That is, now we have a lot of parameterization that exists, but which one should we choose? Because each of them, they give a different trade-off between the performance and the ratio of compression. That means if we make a neural network that is too sparse, maybe you will lose a lot of accuracy, lots of the loss of performance of your model. So that's a question that we would like to study. And with that, first, it's very natural to look at this problem as an approximation of a matrix by a butterfly parameterization, because the butterfly factor, their support is fixed and a structure. So we think that FSMF it can be very useful here. And if we look at the formalist of the problem, so we minimize the distance between a target matrix A and products of some butterfly factor. It's simply a generalized version of FSMF, now with multiple factors, but their support are very structured. And this problem, in fact, it's had been proposed. There are several algorithms that have been proposed for it. It's based on the principle of hierarchical factorizations, and all the algorithms had the same name, called butterfly algorithms. However, they had no theoretical guarantee about the solution that they obtained. And for us, it's also interesting to look at this problem, because when the infimums of this optimization problem 1 equal to 0, that's corresponding exactly the hypothesis class of matrix that we're trying to learn, because we replace a dense matrices by products of some sparse factor. So actually we change the hypothesis class that we are learning. Instead of learning on a dense matrix, we're learning on the set B. And so our results is we have 2 main results. So the first one is actually the butterfly algorithm that have been proposed and studied in the literature. It is an approximate algorithms in the sense that if E star is the best approximation, then the solution obtained by the butterfly algorithms gel distance that is smaller than a constant times E star, and this constant depend on L. So the number of factor that is that we want to approximate the matrix A with. For example, if L equal to 2, then this constant is equal to 1. So we have the exact optimal solution. But for L bigger than 2, then this constant grow. But still, if L is a constant, then this is constant, and that is good enough for it. Also using the same technique, we also obtain an algebraic description of the set B. Okay, so the set B defined here. Oof. Sorry. So in word, it say that the set B it can be described by we have a lot of partition of the matrix, and for each partition we have some submatrices, and these submatrices had to be low rank. So this is the so-called complementary low rank matrices in the literature, and the partitions of the matrix and the ranks of each submatrices it is controlled by the support that we impose on the butterfly factor. Okay, to sum it up, so in our work, we try to make a link between the problem of sparse matrix factorization and its variant FSMF with sparse neural networks. We propose some necessary and/or sufficient condition for the existence of optimal solution for sparse neural networks. And we also study several related questions with the so-called butterfly parameterization. So in the future, we really like to know if there exists a better algorithm to decide the ill-posedness of FSMF, let's say to decide the closedness of the set Pij, because now the algorithm is doubly exponential, so it's not very practical algorithm to use. And also we would like to fully characterize for weak support the problem of sparse neural networks. It admit an optimal solutions. So thank you everyone for your attention. Thank you for the invitation to present in the seminar. So here's something that may be relevant for those of you that is interesting. So the first one is the software that called PyForce. So we implement the algorithm that I showed in the slide, and the other two it correspond to the first and the second section of the talks. The third one, the papers is still written, so there's no link yet. So again, thank you everyone, and I will be very grateful to have any question and answer. Thank you.